Welcome back, guys. Today we're going to be moving into another part of our measurement unit, and we're going to be taking a look at surface area and volume of three-dimensional objects. Now, in this first part, or in this first lesson, we're going to be taking a look at surface area, and I've actually broken this lesson into two videos. So in this video, we're going to be looking at the introduction and review of surface area. We're going to be taking a look at some of our area formulas from junior high, and then we're going to get into the surface area of prisms and cylinders. In the second video, we're going to be taking a look at the surface area of pyramids, cones, and spheres, as well as conversions between area units and dimensional changes. All right, so moving on, before we get into the actual area formulas, it's important that we take a look at the objects themselves. Quite often when we're working with surface area and volume, we have a tendency to sometimes mix up certain objects, and that affects the formulas that we choose. So normally in class, I would be giving you these objects and having you sort them into their respective categories. Today, I'm just going to be sorting them on the video, but what I want you to do is be thinking about where these objects are going and why. And then as I'm sorting these, there's going to be some that go into the other category, meaning they don't fit into any of these particular groups. And again, I'll be asking you to think about why that might be. So again, as these are being sorted, ask yourself, where do you think they should be going? Why should they be going there? What attributes do they have in common? Why might they fit into the other category? All right, so here we have them all sorted, and we've got spheres, prisms, cylinders, cones, and pyramids, and we'll get into the other category as we're working through these. Now, first of all, let's take a look at spheres. Spheres is one that we don't typically mix up. When we're talking about something that's spherical in shape, it's circular in shape. Essentially, we think about a ball, baseball, volleyball. Now, in reality, not all of those balls are actually truly spherical. Sometimes we talk about the Earth as being spherical, but it's really not. It's an ellipsoid. But when we have something that's truly spherical, our radius should be the same no matter where we take it from on that sphere. Now, next we're going to get into prisms and cylinders. Now, they're two separate categories, but often we treat them the same because they do have a lot of things in common. So when we're talking about a prism, for example, this is a pentagonal prism. A pentagonal prism is named based on its base. And so the base here is a pentagon, and so that's why it's called a pentagonal prism. Now, when we say base, we're not talking about the bottom of the object because I can orient this object in any different way. The base is the face that gives it its name. And so when I have a prism, you'll notice that I have a pentagon on either end of this prism, and those faces are separated by rectangles. I have a rectangular prism, so I might decide to make this here my base. And so that base here would be a rectangle, and those rectangles are separated by other rectangles. If I wanted to make this the base, it would still be a rectangular prism. Now, when I take a look at another object here, I've got a trapezoidal prism. Notice that I have my opposing faces, or my opposite faces, are a trapezoid. And then those faces are separated by rectangles. So when I have a prism, I have two identical faces. Those are my bases, and they're separated by rectangles. Now, when we look at cylinders, cylinders are really just like a circular prism. So I have my circles on either end, and they're separated by a rectangle. Then we get into pyramids. Now, with pyramids, you'll notice that all of them come to a point. And when we're talking about objects getting mixed up, quite often the ones that get mixed up are a rectangular pyramid and a triangular prism. So with a triangular prism, I have two triangles on either side separated by rectangles. Pyramids all come to a point. And notice it's a rectangular pyramid because my base is a rectangle. All right, now with cones, cones again act very similar to pyramids. They come to a point, but my base is a circle. And again, it doesn't matter how I orient it. Base doesn't necessarily mean bottom. Base is what's giving it its name. Now, if we look in the other category, we have a balloon, a rugby ball, a funnel, and a bucket. Now, the bucket's probably the first one you might have been wondering, well, why is that not in the cylinders? Well, if we take a look at the bucket, the top of the bucket and the bottom of the bucket do not have the same size circles. And that means these are actually tapering in. And so this can't be a cylinder because for it to be a cylinder, both circles have to be the same size. Balloon looks spherical, but it's not an equal radius in all places. Rugby ball just doesn't fit into any of these categories. So it's definitely a 3D object, but it's not one of these base shapes. And then the funnel is actually almost comprised of a cone and a cylinder, but because the two pieces have been merged together, we don't have two clearly defined objects put together. This is not any of those 3D objects. All right, so we're going to take a look at area formulas. Now, these are formulas that you would have learned in previous math classes, and they're ones that you have to have memorized. They are not going to appear on any formula sheet. So first one here, we have a rectangle. Area of a rectangle is length times width. Now, it doesn't matter where you put your length and your width. You might choose to put them here and here, or you might choose to swap them and have length here and width here. But that's our base shape. Area of a rectangle is length times width. Now, when we're talking about area, this is a surface that we could paint or we could cover with wallpaper. So the area is the amount of space that we're painting or covering or coloring. Next one here we have is a square. A square is just a special rectangle, but a square is special in that all the sides are equal, so our area is side squared. And then we have a triangle. Now, triangle is 1/2 base times height. Sometimes you'll also see that as area equals base times height divided by 2. I often don't use this one as much simply because I find that I often forget to divide by 2. So a triangle is just 1/2 of a rectangle. Notice that when we have h, though, that refers to a perpendicular height, meaning that height is making 90 degrees with my base. All right, the next object we have is a circle. Area of a circle is pi r squared, and unlike you might have done in previous classes, we use the pi button. So we don't use 3.14, we use the exact measurement of pi. Parallelogram. Parallelogram is basically just a rectangle tipped on its side, and the formula for a parallelogram is base times height. Again, notice that we are dealing with the perpendicular height. Sometimes you'll be given the slant height. That will come in handy when we're doing surface area, but when we're looking at the area of a parallelogram, we want the perpendicular height. And then the last one here we have is a trapezoid. Now there's different formulas that I've seen. This one here is 1/2 base 1 plus base 2 times height. Quite often I've seen it written as area equals 1/2 times a plus b times height. All that's important for you to know is that the a plus b and the b1 plus b2 are the same thing. We're just adding those two opposite sides together, multiplying by our perpendicular height, and then dividing by 2. So I've also seen it written this way as well. A plus b times height divided by 2. And in junior high, you may have actually built this formula or derived this formula. If you notice, a trapezoid is really just two triangles and a rectangle put together. And when we work with those formulas and put them together, we end up with this trapezoidal formula. All right, so moving along here, we're going to talk about perimeter and circumference. So we talked about area as something that we would paint, so the amount of space that we would paint. Perimeter is the distance around an object. And so when I'm thinking about perimeter, I might be thinking about fencing a yard. I might be thinking about a security officer that's surveying the perimeter, so they're walking around the outside of a building. And so for the perimeter of a rectangle, the perimeter of a rectangle is 2 times length plus 2 times width. Because if I had a rectangle and I want to find the perimeter, so I want to find the distance around the object, I'm just adding up all the lengths. And so that means 2 lengths and 2 widths. So calculating this out, I'm going to have 2 times 7 plus 2 times 12. I could rearrange those and I could go 2 times 12 plus 2 times 7. I'd still get the same answer. And that gives me 14 plus 24. And that gives me a perimeter of 38 centimeters. Now notice here I have 38 centimeters because these are linear measurements, so we don't need a squared or a cubed, it's just centimeters. For circumference, that's the distance around a circle or the perimeter of a circle. the formula is 2 pi r, or you can also write it as just pi times diameter. And again, we're using the pi button. So it's going to be 2 pi times 5, and that gives us 2 times 5 is 10 pi. And since pi is 3.14, multiplying by 10 will give me 31.4 centimeters. Now again, this would be an irrational number on my calculator. If I'm not told how to round, typically I would round to the nearest tenth. All right, so I want you to pause the video here and try some of these practice questions. You're given 3 shapes and you're asked to calculate the area. All right, so let's take a look at these. For the first one, we have a parallelogram, and the area of a parallelogram is base times height. And so our area is 8.5 times 5.2. Notice that we're always looking at the perpendicular height. And then my area is 44.2 meters squared. Notice now we're working with area, so that means our units are squared. For the next one here, we have area equals 1/2 base times height, or base times height divided by 2. So I have 1/2 times 16 times 9 gives me an area of 72 inches squared. Note that the 13 was given there just as a distractor. That's a slant height, and we don't need that for this question. And then the last one, we have the area of a circle is pi r squared. So we have pi times 44 squared gives me an area of 6,082.1 millimeters squared. Now, something that might be important to note here, when we're talking about two-dimensional area calculations or two-dimensional shapes, we call them shapes. When we start getting into surface area and we're working with three-dimensional objects, we call them objects. So 2D is shape and 3D is object. All right, so we're moving on to the second part of this video, and we're going to start looking at the surface area of prisms and cylinders. Before we get into that, we want to actually take a look at what is surface area and what is not surface area, and also take a look at nets and drawing 3D objects. So first of all, let's take a look at examples of surface area. So when we're talking about surface area, we might be talking about calculating how much paint is needed to cover the walls of a room. We're definitely going to be working with units squared. Quite often we might be working with the nets of an object. We might be looking at how much wrapping paper is needed to cover a gift, or the amount of cardboard needed to build a box. Now, some non-examples of surface area. Certainly units cubed is not surface area. Units cubed would relate to volume. A measuring cup relates to capacity. Units might relate to perimeter or just length of an object. And calculating how much water is needed to fill a pool, that's capacity or volume. And then calculating the amount of lumber required to fence a yard. Well, if I'm fencing a yard, that is going to be perimeter. And then the last one here, the amount of carpet needed to cover a floor is 96 feet squared. Quite often I'm asked why this shows up here and not with surface area. Well, when we're looking at the amount of carpet needed to cover a floor, we're just looking at a two-dimensional space. So we're looking at a shape, not an object. So it's area, but it's not surface area. Surface area is for three-dimensional objects. So using those, I want you to see if you can figure out where these might fit. So the first one is calculating the amount of siding needed to side the exterior of a house, calculating the amount of sand needed to fill a playground, predicting the amount of baseboards needed to finish a room, and determining the amount of fondant needed to design a cake. So I'll give you a couple seconds and then I'll put them where they fit. All right, so when we're calculating the amount of siding needed to side the exterior of a house, we're covering the outside surface of the house. So that's definitely surface area. If we're calculating the amount of sand needed to fill a playground, well, this has to do with capacity and volume. So that would fit over here. And then when we're predicting the amount of baseboards needed to finish a room, that's just like fencing our yard. We're just working on the trim of the room, so that would be perimeter, so not surface area. And then the last one, determining the amount of fondant needed to ice a cake. Well, this is that icing that we kind of roll out and fold over the cake, so that would definitely be surface area. All right, so moving on, let's take a look at nets. And so for the first one here, we want to just compare our objects to the nets or match the objects to the nets. So again, I want you to pause the video, think about where these might fit, and then come back and check your answers. All right, so taking a look here, the first one, we've got the 2 circles and a rectangle, so that's going to fit with a cylinder. The next one here, I have a rectangle and then 4 triangles, and I notice if these fold together, they're all going to come to a point. So that's going to go with my rectangular pyramid. I have a bunch of rectangles here, so that's going to relate to my rectangular prism. And the last one, I have a circle and sort of this curved triangle shape. That's going to be a cone. All right, so the next thing I want to take a look at is sketching 3D objects. Now, I certainly don't expect great artwork. I'm not a great artist, but it is important that you can do a basic drawing or a basic sketch of these objects, especially when you're having to label your dimensions. So the first one here is a rectangular prism. This is one that I've struggled with before to draw. And so I'll just show you some of the tricks I've come up with. I know that there's quite a few in your class that are quite artistic and could definitely outdo me on this. Certainly do the best that you can. When I want to draw a rectangular prism, I start by drawing two rectangles that are a little bit offset. And then I connect my vertices. Now, other times what I might do is I might start off by drawing just the rectangle, draw my angled lines, but as you can see, sometimes it doesn't come out quite as nice. Now for the next one here, I've got a cylinder. So you kind of draw an oblong circle, line straight down, and then curved, and then you can label your radius. And if you wanted to draw it sideways, it would just be an oblong circle up and down. Okay. Now for a cone, start off by drawing the starting part of a triangle, and then you can curve. If you want to put that dotted piece in the back, you certainly could. And again, you're labeling your radius. For a sphere, we're drawing the circle, a little bit of a curved space here. And then to give that third dimension, you could put the dotted space in behind, and then a radius. And the last one, this is the one that I often struggle with, is a square-based pyramid. So I start off by drawing a triangle and then an angled triangle in behind. And if you wanted to try to fit in that square-based piece in the back, you certainly could. Okay. Other people I know will show their solids by shading. So they might draw the triangle piece, draw this in here, and then kind of shade this in to give it that third dimension. All right, so hopefully that at least gives you a starting point for drawing your objects. All right, so we're going to jump right into surface area of prisms. Now, when we're finding the surface area of a prism, ultimately all that we're doing is finding the area of all of the faces and adding them up. And so we can do that by drawing all the individual faces. We can draw nets, or we can use formulas. With a rectangular prism, we do have a formula that we can work with. I'm going to start off with drawing the net, and then we'll get into the formulas. All right, so I'm going to start off by drawing my net. And so I've chosen to start with the base of 4.5 and 1.7. And as this unfolds, I would have 4.5 by 2 and 4.5 by 2. And the end pieces would unfold here 1.7 by 2 and 1.7 by 2. And if you notice here, I only have 5 faces, but a rectangular prism has 6 faces. And that's because I've missed my top. So it's really important that you always double check to make sure you have all of your faces included. I'm not looking for these to be drawn to scale, just to have a quick sketch. And we want to label our dimensions. Now, it is important when we get into application questions that you read carefully to see if all of the 6 surfaces are included. If this, for example, was a lidless box or a box that had no top to it, then we would not have to include that top piece and there would only be 5 rectangles that we were drawing. So once we have this drawn out, we want to make sure that we label our sides. So I have 1.7, I have 4.5. Now you could label these all the way throughout or just label the key points. We have 2. Notice that our adjoining sides are the same length. So these 2 pieces will fold together. They'll both be 2 by 2. And again, I'm not looking for them to be drawn to scale. And you can label those on the other side if you like as well. So again, if you want to go through and label every rectangle, you can. If I label just on this end that it's 4.5, I know that every line going down is also 4.5. Now at this point, you don't have to show me all of your formulas. You don't have to show me all of your area calculations. You just have to show what your areas are. So here I'm going 4.5 by 1.7. And if I'm going 4.5 by 1.7, that's going to give me 7.65. And then 4.5 by 2 is 9. And again, I have 7.65, and then I have 9. And if I go 2 times 1.7, I'm going to have 3.4. All right, so now when I add these all up, my total surface area is going to be 40.1 centimeters squared. Again, if you're not asked to round a specific amount, then you're going to round to the nearest tenth. Now, when it comes to rectangular prisms, we actually have a formula as well that we can use. So we have the surface area of a rectangular prism is 2 length times width plus 2 length times height plus 2 times width times height. And again, it doesn't matter what you designate as your length, width, or height. So filling in the information here, I'm going to have 2 times 4.5 times 1.7. I find it easier to actually work downwards. So I'm going to have 2 times 4.5 times 2. And I have 2 times 1.7 times 2 gives me 6.8 and 18.0 and 15.3. And if I total those all up, I'm again going to have 40.1 centimeters squared. So whether you use the formula or whether you use the nets is totally up to you unless the question specifically asks you for a certain method. All right, moving on to our next example here, we have a triangular prism. Now with triangular prisms, it's really important for you to know that there are 3 types of triangles. We can have an equilateral triangle, meaning all sides are the same. If it's an equilateral triangular prism, then that means all 3 rectangles are the same. That's kind of like a bonus because we don't have to do as many calculations. Now we can also have an isosceles triangular prism, meaning my 2 sides are the same, my base is different, so that would mean 2 rectangles are the same and the third one is different. And I can also have a scalene triangle. And a scalene triangle means all 3 sides are different. That means all 3 rectangles are different. So if I wanted to calculate this using a net, I would start by drawing out my base of 3.6 by 5.9, draw out my end triangles, and my other 2 rectangles. So notice there's 5 sides when we're dealing with a triangular prism. And again, I would label all of my dimensions. So I've got 5.9, and I have 3.6. And we're told that this side is also 3.6, and my height is 3.2. And so because this is 3.6 and this is 3.6, I know this is an equilateral triangle, meaning that all of my rectangles are going to be the same. So filling in my measurements here, 5.9 times 3.6 is 21.24. That's going to be the same for all 3. And then the area of the triangle is base times height divided by 2. That gives me 5.76 and 5.76. Now these are decimal answers, but we do want to make sure that we keep everything exact in our calculator. Now if I add all of that up together, my total surface area is 75.2 centimeters squared. Okay, or if I want to go a little more detailed, I could write 75.24 centimeters squared. Now, when it comes to a triangular prism, there is no magic formula that we can use. Okay, I often get that question, well, what's the formula for the surface area of a triangular prism? There is no magic formula. This one here, you have to find the area of all the faces and add them up. So some people might find it easier to actually just draw out the faces. And so I have 2 triangles. So I have a triangle that's 3.6 by 3.2, and I have 2 of them. So area would be base times height divided by 2, or 1/2 base times height, which would be 1/2 times 3.6 times 3.2. And because there's 2 of them, we would multiply by 2, and that would give me 11.52 centimeters squared. And then for the rectangles, because this was an equilateral triangle, all 3 rectangles are the same size. So we have 5.9 by 3.6, and we have 3 of them. So area would be length times width times 3. So I would have 5.9 times 3.6 times 3, which gives me 63.72 centimeters squared. And when I add those together, my total surface area will again be 75.2 or 75.24 centimeters squared. All right, so now I want to give you a chance to practice. I want you to pause the video, try these 2 questions on your own, and then come back and check your answers. Note when you're doing this that it asks you to draw a net. So we're not using formulas for this question, we're going to draw a net. All right, pause the video and come on back. All right, so taking a look at this first question here, we've drawn out the net or sketched out the net here. Again, I've labeled my dimensions. So I have two rectangles that are 8 by 4, two rectangles that are 8 by 2, and then two rectangles that are 4 by 2. And so again, you don't have to show all of your area calculations. If you have an 8 and a 4 and you wrote 32, I can interpret from that that you went 8 times 4 to get 32. If you wrote 8 and 4 and wrote 16, then I know that you've made some kind of calculation error. All right, now when we add these all up, I should get a total surface area of 112 inches squared. There was no decimal to worry about, so I didn't put it to the nearest tenth. Now for a triangular prism, this is an isosceles triangular prism. That means two sides are the same and the base is different. But if you notice, I don't have that slant calculation there, that slant measurement there, so I have to use the Pythagorean theorem to find it. So I'm going to have x equals the square root of 15 squared plus 5 squared, gives me the square root of 250. If I reduce that, that's 5 root 10. Now it does round to 15.8, but we have to keep it exact on our calculator. So you can either use 5 root 10 on your calculator or root 250, but we want to make sure everything stays exact. All right, now again, because there's no formula, I have to draw out my nets. And so I'm going to have my 3 rectangles and my 2 triangles. Now I'm going to pull up the calculator here so I can show you how you can do this on your calculator and avoid having those rounding errors. So again, whether you do the 5 root 10 or the root 250 is totally up to you. But our first step had been to go 15 squared, the square root of 15 squared plus 5 squared, and that gave me 15.8. I'm going to keep that number exact in my calculator, and I'm going to multiply by 20. And I know that there's 2 of those, so I'm going to multiply by 2, and then I can add in the other numbers that are not rounded numbers. So I have 200 and 75 and 75, and I end up with a total surface area of 982.5 centimeters squared. All right, so we're going to move on to cylinders. And like I said, cylinders are really just like a circular prism. So we have a circle on either end and it's separated by a rectangle. So we're going to start off with the formula here. The surface area of a cylinder is 2 pi r squared plus 2 pi r h. But it's not enough to know the formula. It's really important that you understand where that formula is coming from. And so if I sketch my net for a cylinder, you'll notice that it's made up of 2 circles and a rectangle. Now, I've also seen people that sketch it this way as well, where they have the rectangle and the 2 circles like this. It really doesn't matter as long as you have your 2 circles and your rectangle. All right, so filling in the information that I know from previous formulas, I know that the area of a circle is pi r squared. And I know that the area of a rectangle is length times width. Well, this length right here is the same as the distance around the can or the cylinder. So if you think about taking a label off of a can, that label goes all the way around the perimeter of the circle, which is the circumference, and circumference of a circle is 2 pi r. And then the height of my cylinder would be here. So 2 pi r is my length times my height, or my width, becomes 2 pi r h. Now this is important because sometimes when we're working with application questions, we might be told that it's an open top can. Well, that would mean now we change our formula to just pi r squared plus 2 pi r h because there's no circle. Or maybe I'm looking at a grain bin that's been damaged and I'm talking about that lateral surface being damaged and I don't really care about the circles, well then I'm just going to use the 2 pi r h. So again, it's really important that you know where that formula is coming from. So taking a look at our example here, we have a cylinder with a radius of 1.5 centimeters and a height of 6.2. So we'll start off by writing out our formula. So 2 pi r squared plus 2 pi r h, and we substitute in. So my expectation is that you're writing your formula and you're showing your substitutions and then showing your answer with units. So 2 pi times 1.5 squared plus 2 pi times 1.5 times 6.2. And at this point, you can put everything into your calculator. I don't expect you to show me step by step how you got to your answer. Once you can put it all into your calculator in one step, I'm okay with that. So we're going to have 2 second function pi 1.5 squared plus 2 pi times 1.5 times 6.2. And we end up with 72.6 centimeters squared. by putting it into our calculator in one step, that helps avoid some of those rounding errors that can happen when we try to do it step by step and then add it together. All right, so once again, I'm going to have you pause the video, try solving this question, and then come on back. All right, so taking a look at this question, again, we've written out the formula 2 pi r squared plus 2 pi r h, and then we've substituted in our radius and our height, and we have our final answer is 100.5 centimeters squared. Notice that I'm not writing the units anywhere until the very end because that just gets messy in the problem. So make sure you include your units, but you don't need to worry about doing that until the very end. So we're going to take a look at one more example, and that has to do with a Quonset. So the question asks us, how much corrugated steel will be needed to cover a Quonset that is 20 feet wide by 48 feet long if both the front and the back are covered, except for a door that is 8 feet tall by 7 feet wide? So we're not worrying about a floor, okay? Likely it's a concrete floor or a dirt floor, but we just need to worry about the corrugated steel that's being used for this Quonset. So I want you to pause the video, try this on your own, and then come on back. Taking a look at this question here, we have this object here that's really just a cylinder that's been cut in half. So we have this cylinder and only half of it, it's like picturing half of it being below the surface. We don't need that piece. And so we just have to find this surface area here. So really what we're doing is we're taking the surface area of a cylinder and we're cutting it in half. So 2 pi r squared plus 2 pi r h divided by 2. And then because the door is not included, we're going to subtract the area of the door. So substituting everything in, we've got 2 pi times 10 squared plus 2 pi times 10 times 48. We're going to take that and divide by 2 and then subtract the area of the door, which is 56. So again, I'm going to show you this on the calculator as we go. So we're going to have 2 pi. I'm going to do this in multiple steps. I'm not going to plug it in all in one step here. So 2 pi times 10 squared plus 2 pi times 10 times 48. Going to hit enter. That gives me 3,644.25. I'm going to divide by 2. So now I've cut that in half, and then I subtract my door. It's important that you pay attention to order of operations as you're doing this. So we get 1,766.1 feet squared. Now you can put this in your calculator in one step. I wouldn't recommend it. It does get quite messy, but you have to just remember all of your brackets. So we start off with a bracket. We've got 2 pi times 10 squared plus 2 pi times 10 times 48. This is where you got to remember to close your brackets, and then you can divide by 2, and then you can subtract 56. Now, if you're doing this all in one step and you didn't know 7 times 8 was 56, you can certainly do that part in brackets as well, and we'll still get 1,766.1, but notice there's way more chance for making silly mistakes and way more numbers that you have to check before you hit enter. All right, so there are some examples that we have for surface area of prisms and cylinders. In the Part B video, we're going to be taking a look at the surface area of pyramids, cones, and spheres, and then we're also going to be looking at unit conversions and dimensional changes. All right, guys, have a great day, and we'll see you soon.